All right. I will attempt to begin class with a word of prayer. Dear Father, we thank you for this day, and I thank you for this class, and just ask that you guide our steps, help us to understand a little bit more about conformal mapping today, Lord. In your name I pray, Lord Jesus. Amen. All right, so one of the things I wanted to show you, which is just kind of fun, is what this is a sphere which actually puts the conformal mapping, the stereographic projection into play. So although it's technically for a slightly different stereographic projection than the one we did, there's another stereographic projection where you put the North Pole just touching, or no, the South Pole just touches the plane, and the North Pole is like above it. And so the equator is not intersecting the Riemann sphere. There's like two different ones. So this one's like the other one, but it's basically the same. It's the same story essentially. And so I mentioned that it's a conformal map, right? So like it actually preserves the angle between curves in the plane if you study their image up on the Riemann sphere. And so like what this is it's the grid on the complex plane, like the XY coordinate grid, projected up to the sphere. If you can kind of see how that, if you can, I mean, that's what's going on. So like the grid on the XY plane projected up into the up in the sphere. See that? You see it close up. But where does this come from? I believe it's 3D. That probably is going to be all blurry and junk, but 3D printing. Now we, fortunately, are in a second story, and as you know, this building was built over decades. And at the time this floor was built, we still believed in light switches. So let's see here if I can get this to work. All right. So if you can see this, let me see if I can get this to work here. All right. So if I put the light right at the, maybe I can do better up here. If I put the light right at the north pole, then you'll be able to see. Man, there's still a lot of light coming in from the hallway. That's annoying. Once our eyes get acclimated, you'll be able to see the grid, though. I don't know if you guys can see it or not.
It's darker in that one.
Where? Which one?
In the behind.
Over here?
Or even on the one.
Try not to run into stuff. It's still not quite dark enough in here. I guess we can do here. Oh, look at this. Here we go. See that?
Whoa. Oh.
So that's the projection with light rays. So as you can see, you know, the grid on the whiteboard is projecting. Well, I guess you can't really entirely tell, but it would project up onto this little sphere. That is a stereographic projection. It is preserving the 90-degree angle between the. That probably didn't show up in the video. But anyway, you guys are here, so if you really want to see these things, you have to come to Liberty and, you know, pay the big bucks, sit in these chairs. All right, there we go. So that's the stereographic projection, and the fact that area is not preserved is like pretty obvious. But anyway, put that away. Yeah, I got it's like a 3D printed thing. I bought it years ago, and a colleague of mine gave me this wonderful Liberty pen. Like, you really do need like a point source of light to make it work well. All right, so there's that. All right, let's see if we can work an example today. Example 1. So, all right. I'm going to start with a solution of Laplace's equation here, and let's say we want phi equal to, not phi, I use psi over here, psi equals to 10 here, and psi equals to 20 over here on the edges, right? So can we write down a solution to Laplace's equation on this quarter plane? What should we do? We should use, basically we can just use psi of w is equal to, you know, a arg a arg of, well, all right, my bad. Let me stay out of trouble for a change. Let's try instead to put 10 up here, and I don't know, put 0 down here. How about that for psi? All right, and we'll try to solve it. What? Why are there flies in here? Anyway, in this wedge. All right. So here we're talking, you know, pi over 4 this way, pi over 4 that way. All right. So it's a quarter plane. But we ought to be able to make this happen with a arg w plus b for appropriate choice of a and b, right? Okay, so if we, for example, we could pick this point and that point to fix our values. So I'm going to feed it like e to the pi I over 4, right? So that would be a times pi over 4 plus b, and then psi of e to the minus pi I over 4 would be minus a pi over 4 plus b, right? You guys with me? I hope. All right, so then if I all right. Now this, of course, is equal to, by assumption, 10, and this one's equal to 0 by assumption, right? So when we add these, we get 2b equals to 10, right? I'll put plus here. And when we subtract them, what do we get? We get a pi over 2, right, is equal to 10. So therefore, b equals 5 apparently, and a is equal to 20 over pi. Okay, so lo and behold, we have this solution to Laplace's equation. We have psi of w equals to 20 over pi, and our w plus 5. All right. Now, I can be a little bit more precise. I can write this. This is u plus iv, and we're going to get 20 over pi. Actually, we can use inverse tangent in the current context, v over u plus 5. All right? So my question then is, let's use this template solution, and let's get some mileage out of it. Let's do a few different things with this, all right? But to start with, let's look at a relatively simple map. F of z equals to iz, right? So what's that make the inverse map? F inverse of w equals to what? W over I, right? Or if you like, more to the point, e to the minus pi I over 2 times w, right? So what does that do? Put it into words. What does this do? This rotates w pi over 2 clockwise, right? So if I call this, I think my language I was using last time, before I spent 8 minutes looking for a PDF last class. 8 minutes. I was like, after I looked back, I was like, I am sick. I am really sick, apparently. I don't usually just space out for 8 minutes looking for a PDF. Anyway, so T is that. And the inverse image of this wedge T is what? So you take it and you rotate pi over 2 clockwise, I think. So it should be, I think it's down here, right? If I haven't done it wrong. We'll find out soon. So I believe this would be, I'd called it S, the inverse image under the inverse map of Ft, down here, right? And if I was more judicious with my color coding, it should be the case that, like this is the red one, I think. And this is the blue one, I think. Like that. All right. Now we can double check my work here, right? We could double check my work by, say, so of course if you multiply by e to the minus pi over 2, this takes you to where? 3 pi minus 3 pi over 4, which is over here, right? 3 pi over 4, yep, minus 3 pi over 4. And if I multiply e to the i pi over 4 by e to the minus pi over 2, I get e to the minus pi over 4, which is here. So it is literally what I'm saying. It just rotates pi over 2 that way. On the flip side, if I take this and I multiply by I, what does it do? The opposite, right? It rotates this up 90 degrees. Brrr. Junk. All right, great. So my argument, what I'm trying to tell you guys, is I can take this solution over here, all right, that we set up in the W plane, and I can get a corresponding solution over here. Now, in some sense, this is kind of dumb, because you could have just done the same thing we did over there, over here to start with, and avoided this whole mapping thing, right? But I'm trying to illustrate the idea with a simple example to start with, at least. So over here, I build phi of z as equal to psi of f of c. All right, and in this case, we've got phi of x plus iy equal to psi of, well, I times x plus iy, which is what? Psi of minus y plus ix. All right? You guys with me? So then what can we let's get to the details here, right? So what does that mean in terms of inverse tangent and stuff? So we get the solution phi of x plus iy equal to 20 over pi, all right, inverse tangent of what? X over negative y. So how are you, what's your logic process there? You're saying, you look at this, right? And I'm gonna erase this bit right here. Is that okay, guys? I'm erasing this comment. So this tells me, looking at it, okay, so u is minus y, v is x. I'm putting w with those choices for the real and imaginary parts. And so what you just told me was I do v, which is x, right, divided by minus y. And then, of course, what's left? Plus 5. And there you go. That solves Laplace's equation on this with 10 as the value here and 0 as the value there. Just like that. how, let's see here, what else could we do? What if we, well, that's fine. Anyway, this is a good example. So that's the technique, is basically just this. You write the solution over in the W plane, find where it came from, and then that allows you to write a solution over here. Now, in practice, what you start with is something complicated over here. You figure out a way to map it to something less complicated over there, and then you write the solution back over here. So like, I think I have an example. And annoyingly, I can't find the PDF of this. I have looked. So I'll try to scan at least a PDF of my boring black and white copy of this, but if you look at the video I posted last time, it's got color. So yeah, it should be better. So I need to do some archaeology this weekend and open all my boxes and try to find my stack of stuff from when I taught this course in Alabama. All right. So let's see here. All right. Let's try to look at example 2. And so I'll show you what we're after. So we're gonna try to reconstruct the magic here, even though I don't have the colors. So we've got a circle here. Our target is to figure out Laplace's. We're trying to find the solution of Laplace's equation on this disk here, okay? And so here's point 1, it's in the middle, 2's there, it goes to the origin. This point up here is like 1 plus I. This point down here is 1 minus I for what it's worth. And I want to find, well, I'm not going to find it. I'm going to give you the formula for F that takes this and maps it over to actually a line. We'll figure out what that line is here in a second. But the mapping that we're given is F of Z is equal to 2I over Z plus 1. And I'll try to explain where that, maybe we'll understand how we could have come up with that map once. I mean, perhaps as we work this out, we'll come to an understanding of how it is we could have engineered this map to make this happen, you know? All right? So, because we'd like to, one of our goals for today is to figure out how to map basically a disk to a half plane. That's more or less what we're after. If we can do that, that's a pretty good example. If we can master that example, I'll feel happy. We've done something. All right, so this one here. Oh no. Oh no. Where does F of 0 map? So this is 0, right? And that's 2I over 0 plus 1, also known as come on, you can say it. It's safe here.
Undefined.
No, no, no. This is where you're allowed to say equals infinity.
Okay.
Yeah, I don't require any limit or anything. It's just equals infinity. Like this is, I know, right? Like,
Not infinity I.
nope, just infinity. There's only one infinity. I know, right? Just infinity.
I thought some infinity had another infinity.
Well, you thought wrong.
Yours
Let's see
was
here.
reals.
That's a different kind of infinity. So this is so any topological space, if you have a topological space, you can take a point and form what's called the one-point compactification of that space. And that's what's going on here. So the one point is the one point which is attached to the plane is infinity. But it is just one point. There are, I suppose, 2-point compactifications, but I don't know as much about those. But like you can look at the real line with plus and minus infinity adjoined, but I'm not ready to talk about that at the moment. So 2 plus f of 2 is 1 plus I. f of 1 plus I, don't do that. It's going to catch the 2I over 1 plus I plus 1, which is 2I times 1 minus I over 2 plus 1 multiplying by the conjugate of the denominator. I get 1 squared plus 1 squared, which is 2 downstairs. The 2's, they be canceling, and then I get plus 1. I think it's 2 plus I. Okay, good. That's what I got in notes. And likewise, you can do the arithmetic here. F of 1 minus I is equal to, it works out to I. All right. Now, there's a theorem, right, which it took me an hour to prove, that a fractional linear transformation maps circles, generalized circles to generalized circles. And part of that, when you go through the proof, is that if your circle has the origin in it, it will map to a line, because it has to go to infinity. So it's unavoidable that we have a line. And so since we have a line, by the theory that I haven't worked out, sorry, but since we have a line, we also have 1, 2, 3 points on a line, which is more than enough to fix the line, right? But let me just do some color coding here, show you which one went where and how this goes. So 2, this guy, where did it go to? 1 plus I. So there's where this was f of 2, it was here. And then, man, f of 1 plus I, where'd that go? 2 plus I, so that's over here. All right. And then f1 minus I, sorry I'm not going faster, this is as fast as I go today. You're like, you can be sick all the time, this isn't bad, right? I know. You're horrible people, how dare you. So, should I wear black to differential equations tomorrow, what do you think? I should come in and I should tell everyone, like, you guys, you murdered differential equations. I'm mourning it now.
Yes.
You've murdered it. You've killed it. I'm so sad. I should shave my head too, just to complete it, you know.
You should send out an email saying so, guys.
No, it's fine. I'll feign happiness. It's okay. I can do it. All right, the interior, all right, so the other part of if it's a conformal map, if it's a complex differentiable map, the Jacobian of the map, what is it? So just, point of order here. The Jacobian of a complex differentiable map has the form ux, vx, uy, vy, right? Which, because it's Cauchy-Riemann equations, we've got ux, uy minus uy, right? And so what's the determinant of the Jacobian of a complex differentiable map look like? What is it? Well, it's ux squared, right? Plus uy squared, which, if you look at it, is exactly, I think if you work it out, it is actually the magnitude of f prime of z squared. Because f of z is ux plus I vx, and then vx is minus uy, so the magnitude of that is ux squared plus uy squared, because the minus in the Cauchy-Riemann equation gets eaten up in the magnitude calculation. No, there's a deeper truth here, though. So in advanced calculus, or wherever you study your multivariate calculus needs, you learn that if you have a transformation of the plane and the determinant, or more generally, if you have the transformation from Rn to Rn, and your mapping has a Jacobian, your mapping is differentiable, and the determinant of the Jacobian mapping is positive, that means that it maintains the orientation of sets that it maps. So like for 3 dimensions, if you put in a right-handed triple, right, you have 2 vectors whose cross product is the 3rd vector. Then you map that through such a mapping with a positive determinant Jacobian. You'll get out a triple of vectors, which again is a right-handed, in the right-handed sense. So if you take the cross product of the first 2, image of the first 2, it'll be in the direction of the image of the 3rd. All that means here is that it maintains the orientation of regions that it maps. So like what this ends up meaning is that the boundary in the positive sense will be maintained as you go under a complex differentiable map. So the question is, if we want to think of the region as the interior of this disk, what direction, how do we have to orient the boundary of the disk? Do you remember the story? We have to think about a little dude walking along the edge. He has to be, the inside has to be on his left. That's how we positively orient a shape. So in other words, it has to be counterclockwise. So like the positive orientation here, oh man, is like this, all right? So we begin our journey at 1 minus I, and what have I done? Good night, look at that. You guys, come on. Don't let me do this. Seriously, come on, come on. Ay, ay, ay. Right? Okay. So, start of the journey, middle point, end, right? And the same is true over here. We'd be orienting. So the question is, you know, if this is the orientation, here, then here, then here, where is the region that we're forming the boundary of? If that's on the left, as you're walking in the positive sense along the edge of the region, are we in the upper half plane or the lower half plane? The upper, right. So what I'm pointing out here is that the interior of this disk, all right, it maps up to here. All right. So, all right, so now we have an interesting map. This is a pretty interesting map, right? We're mapping a disk to a half plane in a kind of non-trivial way. I think this is kind of an interesting example, isn't it? So now my question for you guys is, do you think we can come up with a solution on this half plane, which is interesting, that maybe we can map back over to here? Let me see if I do it in the notes. I don't think my example 4 does that actually. Goodness gracious. Well, I'm probably going to get the projector out to look at the other 2 examples. But I want to finish working this one out by hand though. Because this is not in the, I mean, this is in the PDF that I'm going to share with you guys, but it's not, what we're about to do is not in there, okay? So, and this I just made that up today. So, all right.
In what sense would we get a negative determinant? We were talking about positive determinants.
Oh, sure. So a thing with a negative determinant, for example, you can have something like this: f of x comma y equal to, well, let's keep it complex, right? X plus iy equal to x minus iy. Then the Jacobian of f would be like 1, 0, 0, minus 1, I think. And so the determinant of the Jacobian of that function is minus 1. Because that's not a complex differentiable map, right? That's our quintessential antiholomorphic map. So antiholomorphic maps, I think, will have negative determinants, for instance. But there are tons and tons of mappings which have a Jacobian which is like a negative determinant. That just means that it's like locally ripping the function inside out. I mean, the surface inside out in some sense. It's like flipping it over or something. You could think of it that way. All right, I digress. So how about if we were to, let's see if we can do this. I mean, we can try and see what happens, I guess. This seems like, well, that's kind of famous last words with me here lately. But what if we were to attempt to put over here psi equals to 1, and then from here to here psi equals to 2, and then from here to here psi equals to 3, and then over here psi equals to 4. Could we do that? And if we did that, would it even be a reasonable thing to try? Like, where would those, I guess I need to think for a second here. Let me do some color coding. Oh, man. For instance, this bit here between the green and the red, where does that come from? It comes from over here, right? And over here, I mean, infinity's over here, but it's also over here. So I guess see if I can. All right, so from the red to the blue, that would be this piece. And then, well, instead, let me not use orange there. Let me use like red, I guess. I guess I can use the, I'll use this one. So I probably need to put, well, I don't know. That's my question. I'm not, I get, oh, okay. So I think I can put, all right, so from the blue to infinity is this piece, and then from the green to infinity is this piece. So I think this will make sense. Yeah. Okay, so you guys help me out. What's the formula for the solution to Laplace's equation up here? Psi w equal to what?
Looks like you'll need 3 args and a constant.
Right, so we do, let's say, a arg of w minus 1 plus I, right? Plus b arg of w oh, my bad. I better be careful. It's not 1 minus, the question is what's that point? I'm a dummy. Like, oops, it matters what these are. That's I. It's what is it? It's what the value is in the w plane that figures into this, right? Not where it came from, but where it's going, which were 1 plus I for this is I. Got too much going on in here. So that one's I. This one is 1 plus I, and this one was 2 plus I. And for that reason, I write w minus I here, w minus 1 minus I there, and c arg w minus 2 minus I over here. And as you guys told me, add a constant over there for good measure. I regret making all of these constants non-zero, but all right. All right, so I'm not going to go through that, but we could solve it and find A, B, C, and D to make this happen, right? It's clear what to do. Now that I think the setup was something we haven't done yet, because before we had on the axis, so I think I'm giving you something beyond what we talked about already, right? So that would be, once we, plug in the data and choose appropriate constants for A, B, C, and D to make us get psi equals 1, psi equals 2, psi equals 3, psi equals 4, that will be a solution to the Laplace's equation on that upper half plane, right? And then we can use that to solve Laplace's equation over here with the following. The solution, psi of z, is just psi of f of z, which is, 2i over z plus 1. That, by this construction, is going to solve Laplace's equation on the disk and put, phi equal to 3 here, and phi equal to 2 here, and phi equals to 1 over here, and phi equals to 4 up here. This is the genius of conformal mapping. Because writing down a solution to Laplace's equation which achieved these 4 aims directly on the disk would be a formidable task. This is still troublesome, but it is straightforward what we have to do, right? So I'll do a little bit more. So we have to, in order to implement this, leaving the task of finding A, B, C, D aside, let's work it out. So we've got 2i over z, right? Which is what? That's 2i divided by x plus iy plus 1, which is 2i times x minus iy divided by x squared plus y squared plus 1, which is what we got here. We've got ourselves, I'll put some parentheses, 1 plus 2y divided by x squared plus y squared plus I times what? 2x over x squared plus y squared, right? Did I do it right? I squared is minus I squared is 1. That's why I got this plus 2i. 2i times I is minus I squared 2y. And then I get the 2ix, which gives me this piece over here. So my point is that we're now looking at psi of, I guess I can, I'll complete the, I'll make a common denominator just for kicks. So we've got x squared plus y squared plus 2y divided by x squared plus y squared plus I times 2x over x squared plus y squared. So there you go. That's the u and the v, right? Here's your u. Here's your v. And then you would basically put those up into, well, anyway, let me not, I'm not going to really add much goodness to this discussion by writing that out, so I'm not going to do that. Any questions? No? Whew. Come on. Sorry, I don't have your homework graded yet. I'd like to have had that graded, but kind of struggling at the moment. All right, let's see if I can find that. I'll probably have to go back to Canvas. I don't remember. Oh. Rats. I don't have a PDF of that. All right. Desperate times call for desperate measures. Make sure I'm not on the school internet. Let's see here, Wi-Fi off. First recipe for success, do not rely on Liberty Wi-Fi. Do 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 do. All right. Oh man.
Dr. Cook, can I have one of your tissues? Or a couple? Oh gosh. Thank you. Well, one of them broke. So I kind of got.
All right, guys. Oh, it won't take me long here. I'm almost done.
You.
Wait, what's happening? Is the laughing begun again?
Just keep trying.
Ah.
It's because of all of the weather.
Sure.
It's so hot though.
How come none of us
What
are
do you mean it's
sizzling?
hot? It should be illegal to be this hot.
Maybe it's the weather.
How come you're It's the pressure.
It's just September.
And I'm coughing because I got pretzels stuck in my throat.
You got-
There's the truth.
You got pretzels stuck in your throat. That's interesting. All right. Now we're at the mercy of the email.
You should have just had something like Dr. Schwartis and you could just project it. You should just play the YouTube video where you taught this lady.
What's that?
You should just play the YouTube video where you taught this paper.
Just play the YouTube video.
That'd be so
That'd
funny.
be so funny.
You sit in the back, or you stand next to it and pause and play it.
Then I can make a. Then I could do a copyright strike on myself.
Yeah, you should do one of those where you pre-record and then
Interesting.
you talk to yourself on the screen and then you talk back.
If I did this every year, then we could, after like 10 years, have like a tenfold inception. You know.
Would that be such plagiarism?
Self-plagiarism.
If you're citing.
Self-plagiarism. What is self-plagiarism? What does that even mean?
It's something
You're just
it's something you can get points off for.
Something you can take points off
I
for?
cited
No, it's
myself
if
in
you submit
papers.
the same assignment, like the same paper for multiple assignments, because then you're doing half the work, which I think is smart, but apparently it's cheating.
I don't think that's cheating. I think that's just time management.
I cite, as long as you just cite your own paper.
You're just doing the
I
exact
cite
same thing.
my
over and
own
over.
stuff before.
That's a paper
Or
I
like if I
don't
have
wanna
to
do
like
in
build, if I have
place.
essays built off of the previous essays, you have to.
Doesn't matter if-
Plagiarize yourself, I said, we still wrote it. And it's dumb to make you reword it because they assigned you.
Besides that.
All right, one thing.
I guess like one thing to further your ideas, like think of something like
Get 6 Shane, I sit behind you and open up classes. I don't have enough time to get sick either. Trust me.
I'm not sick.
Come on. All right.
change.
So, oh man. Now we're gonna have to wait 5 minutes for this thing to work.
She's gonna cough on you. That. She gets some sick. Cough something.
All right, so one of the things, come on.
You're already sick.
So if you, do you guys have any questions about the quiz while we're waiting for this, or
Oh, that kind of scared
Is there
me.
anything we should prepare for?
you should probably do the quiz?
I mean, what? We're turning in the quiz. It's a take-home quiz?
Yes! Shane, it's on Canvas.
I did
Ah.
see an email.
Shane, 2 weeks ago.
It's
Yes.
been
It's been on.
it's been there all along.
Here, take this. That's yours.
So, all right, guys. So this is some theory of the fractional linear transformation I should have done last time, and so let's talk through it. First of all, where did that condition? Why is it needed? You know, AD minus BC is not equal to 0. Is this a differentiable? Is AZ plus B, CZ plus D complex differentiable? So this is quotient rule. So we do quotient rule, and we get this. And so you see why we have the condition AD minus BC? We have that condition so that the derivative is non-zero. That's why we make that condition, simply that. All right, so the mapping will be conformal, provided that we have the coefficients A and D and B and C such that AD minus BC is not equal to 0. You can also prove that it actually forms what's called a group. So in Math 421 we study groups, right? And a group is a set with an operation which is closed under inversion, and it's an associative operation. And so you can show that the composition of two fractional linear transformations is again a fractional linear transformation. That's actually somewhat easy. But this calculation right here is the thing I couldn't think of off the top of my head, which is you can rewrite this as that, and that is this. So if you look at that, let me give you a rundown here. So you take Z, you dilate it by multiplying by C, then you shift by D, you invert that, then you dilate by multiplying by this non-zero constant, and then you translate by that. So everything I just said is a fractional linear transformation, either an inversion, a dilation, or a translation. So any fractional linear transformation is a composition of translations, dilations, and inversions, like I claimed. And that's the algebra I couldn't think of off the top of my head. My bad. So, and it's not in your notes either. So this is from the guide to Gamelin that I posted in my 1 a.m. announcement, I guess. So here's another nice example. Find a Mobius transformation which takes 1, 2, 3 to 0, I, and infinity respective. So if you want that to be the case, you want a z minus 1 to take the 1 to 0. You want a z minus 3 to map 3 to infinity. And then the value for a will be fixed by f of 2 being I. So I plug that in, and I work it out, and I get that. So these are nice test questions, right? Like find a complex differentiable mapping which maps 1, 2, and 3 to 0, I, and infinity respectively. You should recognize that that's a question about a fractional linear transformation. Here's another example. Here I'm taking infinity to 1, 0 to I, and 0 to infinity. So I say, okay, so then basically we put z minus 3i downstairs to make sure we go to infinity when we plug in 3i. And I don't know what happens, but the top's got to be of the form az plus b. So then I just plug in the other two pieces of data. F of 0 is I, gives me this equation, so b is 3, and f of infinity being 1. See, this is a little bit tricky, all right? So if you want to understand what is f of infinity equal 1 in this algebra, what you do is you rearrange it so that you get division by infinity. And so you get like a plus 3 over infinity, 1 minus 3i over infinity, which shows you that a has to be equal to 1. So that's the arithmetic that turns out to make sense in this context. As I said perhaps this glib arithmetic I've just used with infinity has sown disquiet in your mathematical soul. Yeah. If you'd like, you can replace these with limiting statements if that makes you feel better about it, but it's not really different.
It does.
Okay, well, that makes you feel better, then great. The other thing that I won't make you learn, but I want you to be aware of, is there's something called a cross ratio. So if you want to send Z1, Z2, Z3 to W1, W2, W3, right, that will fix a fractional linear transformation. And if you want to find the formula for it, you just plug those 6 points into this cross ratio and solve for W. This sounds like easy, right? As a formula, it always works, right? No, it's not easy. It's not helpful. It's very unhelpful in certain examples. It would make the two examples I did the previous examples I just did by like just basically making sure that if I've got infinity as an output, I just make sure division by whatever the input is 0 goes to that. Like the examples that I've shown you are way, way easier without using this. I know because I've assigned homework in the past where I've asked students to work it out both ways, and then I regretted it because I had to write the solution. So, yeah. But it also works with infinity. The cross ratio extends to infinity. Like here's an example of that. Here's the theorem I've mentioned a few times. Fractional linear transformation maps circles to circles in the extended plane. I don't have a proof here, and the reason for that is it's actually quite technical. It took me, honestly guys, it took me about 2 solid days of like fussing with algebra to finally get it. It is not easy. Now there is an argument you can make in terms of the interaction between, there's an argument you can make in terms of the interaction between, there it is, yes. In terms of the interaction between the Riemann sphere and the plane, because like every one of the things that we talked about, translation, dilation, inversion, they become something very specific and geometric on the Riemann sphere. And so you can trade the problem of what happens to circles under the complex map for the problem of what happens to their image up on the Riemann sphere. And it turns out that is actually very helpful. But that's kind of what that hour proof I was talking about somewhat gets into, I think. Anyway, as I said, this construction is due to Cayley. The Cayley map is a particular example of a fractional linear transformation. And these are taken from pages 80 to 84 of, I think that's Reinhold Vermeer's book. As I told you guys before, that guy's very impressive. And so this is a very nice, great example for like tests and stuff because it's relatively simple to work with. H of z is z minus I over z plus I for the upper half plane. And so you can prove that it maps the upper half plane to the closed unit disk. Let's see if we can. I've got some color coding going on here. So my claim is that you input 0, you output -1. Can you see that? If I plug in 0, I get minus I over I, which is -1. Great. But I plug in 1, I get minus I. See what happens if I put 1 minus I over 1 plus I? What happens to that? Can you guys simplify that?
Wouldn't that be minus
Wait, yeah,
one?
wouldn't it be -1 at the end because the negatives cancel out, but then the i's?
Oh, yeah, thank you. So that's actually, so those cancel, and you're left with negative I? Is that what it's supposed to do? Oh yeah, this maps to minus I, great. And then what else? Infinity. Notice the dot, see right there. There's your limit. Does that make you feel better? Right there, it's right there. That dash. There, excuse me, if you plug in, you get infinity minus I over infinity plus I, which is 1. You want me to show my work? Infinity plus I over infinity minus I is 1 plus I over infinity, 1 minus I over infinity, but anything over infinity is 0. You guys have been trained to be distrustful of such things. It's good. But it nevertheless is actually a consistent arithmetic which can be worked out. So if this is the orientation, that puts the up on the left if you're a little dude walking along, right? And likewise, that puts the interior of the disk on the left over here. Since it's a complex differentiable map with a positive, positive determinant Jacobian, it maps the interior to the interior of shapes. So that's the map. And all right. So all right. So maybe we could play with this example. So can you guys solve Laplace's equation over here? Let's try to go the other way. What's the solution to Laplace's equation on H? How about this? Phi of z equals to, I don't know, arg 0. How about that? That would give me a solution on here, right? Which is 0 here and pi over there. I think he's called that H, right? All right. And then he's got this H map, which takes you over here to the... Oh, come on. Let's see here. Well, no comment. So let's see here. Where was I? I do know this much. This is this point 1 mapped down here to like minus I, right? And 0. Where did 0 map to?
-1.
Right here. Okay, so this is H of 0 is there. And let's see here. And infinity map to... Okay. So I don't think the value of arg is defined at infinity, technically. Like we don't define the argument at infinity, just like we don't define the argument at 0. But this branch here, right here, I mean this part of the boundary maps to this part. All right. And the other part here maps up here, right? So how can we write down psi of W as a